All right, so my goal today is we're going to talk about something called impulse. So we're just going to impulse is closely related to momentum, which we talked about on Thursday. So I want to introduce this idea of impulse and how it connects to Newton's second law and what we talked about on Thursday. I've got a few questions to think through. I've got some practice problems we'll do, and then you'll have time to work on the syllabus. Um, in this class, did I talk to everybody about? Is there anyone I did not talk about the project? All right, I'll make sure to talk to you guys. That's the plan for today. Homework. So the project sources that we started on Friday or on Thursday. I want those done by Friday evening. So especially those of you who are not juniors, uh, you've got you have plenty of time to do that. But hopefully you've got a good start on that. But I'd like project sources due by Friday. And then on the syllabus that you picked up, as you can see, I've got the first two sections of that syllabus set to be due next Monday. You can do that. All right. Test questions are also posted. I'll hand out the free response part of the test in a little bit, so you can see how you've done on that. But if you want to do test corrections, this would be a good week to get those done before it gets too far in the past. Remember, multiple choice questions are able to be corrected for half credit back. Instructions for how to do that are posted on school. Free response portions can only be corrected up to a 70%. And that would have to be done. All right, go ahead and get out your notes. So what I want to do is I want to connect what we're going to talk about today to Newton's second law. So we're going to talk about this idea called impulse, and we're going to connect it to Newton's second law. Just as a reminder, what we did last time was we defined a concept called momentum. If I remember the symbol we gave for momentum, P. Yep. So, and we defined P as mass times velocity, right? And then we were able to go through each of the laws of motion and talk about how they connected to it, right? So remember the first law, which we usually think about as the law of inertia. So to think about it in terms of momentum, we could say that an object maintains its momentum. And I don't know if I used these words last time, but I'm going to say an object maintains its momentum unless acted on by an impulse. And we'll talk about what an impulse is here in a second. But so this is to make it kind of parallel to the actual first law, right? Remember, first law is an object in motion will stay in motion unless acted on by a net force. So the first law in terms of momentum, we're going to say an object maintains its momentum unless acted on by an impulse. I'll talk about what an impulse is in a second. The second law, remember, we were able to recast it as saying, we're used to saying net force equals ma. We said, in terms of momentum, the net force is equal to delta P divided by delta T. And then we said the third law, which we usually talk about as equal and opposite reactions, we were able to recast that in terms of the idea of conservation of momentum. That if you add up all the momentum at the beginning of an action, right, they should add up to all the momentums at the end of the action. So sum of all p's equals sum of all p primes. Now, what I want to do today is, like I said, I want to define this idea of impulse, and it comes from this second law equation. If I take this second law equation and I just rearrange it a little bit, I can rearrange it as force times delta T equals delta P. And what that's going to mean is this term here is going to be, we're going to define it as impulse. So we're going to find this new thing called impulse. And we're going to give it the symbol J. And impulse is going to be defined as the average force acting on an object times the delta T. So it's roughly equivalent to this. And then if we do that, we can say that impulse causes change in momentum. So in other words, J equals delta P. So the two new equations are this one and this one. Now, impulse is nothing more than just a way of thinking about the overall effect on a force. Remember, we said we want to think about an impulse as the thing that changes its momentum, right? And this is what this equation says: is an impulse causes or is equal to a change in momentum. The reason why it's defined as the average force divided by delta T is because a lot of times when we talk about impulses, impulses do not happen on for a consistent force. So here's an example of an impulse. An example of impulse is if you've got a baseball coming at you and you swing your bat at the baseball, right? You can think about it as the bat applies an impulse to the baseball. However, what a bat does is it doesn't necessarily apply the same force for the same amount of time. Usually what happens is if I were to graph the force over time, right? What would happen is as the baseball hit the bat, the force would kind of increase, like there'd be like a peak in the force, and then it would decrease like this, right? So we're going to say that since the force is always changing, there's a certain average force here. We call this the average force. Sorry, that's a bar. And then the time that this force is acting is that delta T, right? And what we can say is that we can think about that changing force and the time that it acts as providing an impulse that's changing the momentum. So with this in mind, there are two ways that you can get a bigger impulse. What are the two ways you can get a bigger impulse? Don't overthink it. Go ahead. You can either be in contact for more time, or you have a greater average force, right? So if you think about this, right? I mean, and none of this is earth-shattering, right? It makes sense. If you push something harder, it changes momentum more, right? If you pushed it for longer, it would change its momentum more. But this explains things like, for example, why is it important that you follow through on a swing in baseball? Because what are you doing then if you're following through? You're doing what? You're changing what? Which thing? Go ahead, Mark. So you're continuing it. You're continuing that force, which means you're changing its time, right? What's happening is, presumably, you have some average force that you can achieve on the ball. But when you follow through, what you're trying to do is you're trying to increase the amount of time that your bat is in contact with the ball. So if you can keep your average force going for a longer amount of time, you can impart more impulse, right? Okay. So this is the idea of impulse. I'm gonna change over here to some questions we can think about with this. All right. So here's the first question. I'm going to give you here in a moment to discuss it with your partner. But the question is this. Let's imagine we've got two identical, we have two balls that are the same size, same mass, but one of them's a piece of putty and the other one's a bouncy ball, right? So you throw the bouncy ball against a wall, it's going to bounce back, right? You're going to, and then you put the putty against the wall and it sticks. Here's my question. Which one is able to impart a greater impulse? So go ahead and talk to your partner about this. In this case, this first ball hits the ball and bounces off. The second ball hits the wall and sticks. Which one is going to be capable of applying a greater impulse? Tell your partner what you think.
Yeah, I would think. Yeah, that's he's running with the same force and the same thing. I'm winning it and the same thing. Oh yeah, that makes sense. So it would be bigger. Yeah. Yeah.
All right. Nathan, can I ask you what you think? Which one's going to have a bigger impulse? Bouncy ball, why? Okay, so you're saying that the fact that it's bouncy is going to mean that it's in contact with the wall for a greater time? Okay, cool. Ainsley, do you agree?
Yes.
Yes? Same reasoning or different reasoning?
So in comparison to the putty, the putty's going to hit the wall and stick at the end of the time. So with the bouncy ball, you have no time to get it.
Okay, so you're saying that kind of the bouncy ball has to do two things. It's got to stop, but then it's going to get back up, go the other speed, right? Whereas the putty has to stop. Okay, give you that. Now, I would say.
I'd say the bouncy ball because momentum has direction, right?
Yeah.
So if you go from a positive momentum towards the wall to a negative way, your delta T would be greater than the impulse.
Yeah, these are all, yeah, and this is all right. The deal is that Malachi's explanation is the one that I would use. It's the one that makes most sense to me, but this is all right, right? The idea here is that if you've got a bouncy ball, you're going to have to go from positive momentum to negative momentum, right? So going from, let's say, positive 5 meters per second to negative 5 meters per second is a bigger change than going from 5 meters per second to 0, right? So since this one has a bigger change in momentum, and since change in momentum is equal to impulse, this one is going to exert a bigger impulse on the wall, right? Now, some people say something along the lines of, well, isn't this in contact with the wall forever? Right? This is contact in the wall, not forever. Isn't this one in contact with the wall forever? And Ainsley, I think you had an answer to that. What was your answer? Why is this one not in contact forever? Right. Right, yeah, the force, as far as the force is concerned, the force was trying to stop it, right? Once it stopped, the force is stopped. So yes, it's in contact, but it's not applying a force. Now, I wanted to show you a demo with this real quick. So what I've got is, I've got this block, right? And you'll notice this, that ball there cannot bounce, right? Let me just move this just a little bit. So what I want to show you is if I do this right, you'll notice that I can't really get enough impulse to knock over the block on this side, right? I'm going to go ahead and turn this thing around, though. And you'll notice if I turn this around, so first of all, let me just show you, right? You'll see that this side is bouncy, right? It's not aimed correctly, though. So we have this side is bouncy, so I'm going to pull it up about the same distance, right? Now, that wasn't enough. Okay, I should try this ahead of time. All Have impulse to pull it, to knock it over. Now we try the other way because that wasn't really a fair comparison. So if I use the flat end, right, the one that doesn't bounce, and I pull it back the same height, right, there's not enough to knock it over. Because again, a bounce is going to apply a same impulse, or is going to apply a bigger impulse because its momentum has to change. Question about that. Next thing I want you to talk to your partner about. Let's imagine two identical glass vases, right? One lands on a pillow and the other lands on a concrete floor. Which one experiences a longer impulse and which one experiences a larger force? So tell your partner what you think about this one. All right. Val, can I ask you, which one do you think experiences a larger impulse? Okay, why?
Because hypothetically speaking, the base were to like hit the pillow, it would like go up, like it would bounce up here.
Ah, okay. So you're saying that there would, in essence, be a larger momentum change on the pillow because you're okay. You'll have bounce too. Interesting. So I'm gonna. So let me. That's a fair point. Let me give you. Give you some more information. Maybe I'm gonna say that in both cases, there's no bounce, right? Or there's very minimal bounce. There's gonna, like in theory, you could imagine a situation where there is bounce. But I'm going to say that, let's say that in this case there isn't. So, Martin, what would you say in that case?
I was going to say the pillow as well because it'll take longer for the base to go to zero than it would on the concrete.
Okay, so this is an interesting realization. It's something I really want to focus on, right? What does a cushion do? A cushion increases the time that the force acts. So that's a correct realization, right? The purpose of a cushion is a cushion has give to it, right? And the idea is that when the cushion has give to it, it increases the time that the collision happens, right? So I'm going to say that's an important insight, but I'm going to say that the conclusion isn't quite right, right? So, so I'm going to say that the impulse is not large. The impulse is not larger for the one that hit the cushion. What do you think, Leo?
I did think of thinking about it more. I get one. I think that it is the object mission on before because the impulse is not only enough to stop its momentum completely, but it is enough to like shatter the base and like.
Well, you said something really interesting there. You said not only enough for it to stop the base completely, right? And this is something that I want to talk about. Kind of, if something hits the ground, right? In both of these cases, that's what's happening, right? Is that an object is getting stopped completely, right? So what I'm going to say is that in this case, because they're both falling from the same height, they're going to both have the same momentum before they hit the ground, and they both need to stop completely. So if they both have the same momentum and they both stop completely, they're going to have the same change in momentum. So I'm going to say they have the same impulse. But both Leo and Martin are onto something here, in that why is it better to be on the pillow? Not because the pillow has a greater impulse, but because the pillow has what? It has less, who said that? Yeah, go ahead, Mark. It has less force. Why can't it have less force?
Because it's doing it over more time than the concrete, and that means it's
Yeah, so if the idea is if you've got a cushion, right? So we established that if you got a cushion, you increase the time. And the idea is if you will need to have the same impulse in both cases, but I'm able to increase the time, that means I don't need as much force, right? So the point of any sort of cushion from this perspective, right? The point of a cushion is to increase the time over which the force acts. Because if you increase the time, you don't need as much force, right? I like to explain this another way, right? If I were to stand right here, and if I were to slam my head on the table like this, if I were to slam my head on the table, right, that would hurt. That would hurt because what has to happen is my head has to go from moving to not moving instantly, right? Or in a very small amount of time. If I slam my head on the cushion, right, I still have to go from moving to not moving, but since the cushion has give to it, I go from moving to not moving over a greater amount of time, and therefore need less force. That makes sense. This is the same sort of reason as why it's if you if you jump, right, when you hit the ground, you want to bend your knees a little bit. Because if you bend your knees, then you're sort of cushioning your own fall, right? You're increasing the time it takes for your body to come to a stop. You still have to come to a stop. You still have to get the same impulse somehow. But if you can increase the time that you're getting that impulse in, you don't need as much force. If you lock your knees, right, you have to come to a stop instantaneously. If you come to a stop instantaneously or in a very small amount of time, you need a lot more force. All right. What's that? Yes, yes. We're gonna coming up. I think this is next week. We're actually going to do a lab with this, where we're going to try and think about ways that you can keep an egg from breaking. So you probably done an egg drop lab at some point before, but we're going to kind of talk about that a little bit more next week. But this is the idea of what it is. All right, let's put some math to this. So I'm going to hand out a couple practice problems here. When you get this, you can see what you can do with number one. Now, I'll say that basically what I wanted to do is of these three problems, some of them have to do with what we just talked about. Some of them have to do more with what we talked about last time. But I just wanted to kind of give you three practice problems before you get started on your syllabus. So take a look at one and see what you can do with one. The unknowns first. Okay, so just to use our new notation, I'm going to go ahead, instead of V naught and V like usual, I'm going to call them V and V prime, right? So 43 and 56, is that what you had? Are you okay with that? Okay, so time is what? 0.0007. Mass is 0.145. I have one picky but important thing that I don't like here. Let me see what it is. Let's see what it is now. Yeah, Danielle. Well, depending on how you do, you could do it, depending on how you drew your diagram. The way I did it, I've got the initial going forward, the final going backwards. But yeah, you could do it. You could do it either way, depending on how you do it. So this is the only thing, just to make sure, because we kind of got spoiled when we were dealing with energy. We didn't have to deal with direction because we were doing v-squareds, and so it didn't matter. But we're back to it mattering with momentum. So, all right, so that's what we got there. Okay, so what are we going to do with this? Let's see what we're going to do with this. Go ahead, Chris. Yeah, I think that's the best way to do it. So because we're trying to find, at least in part A, we're trying to find impulse, but impulse is just change in momentum, which would be final momentum minus initial momentum. Sorry, I guess let me be consistent and use consistent. Instead of P minus P naught, I'm going to use our new notation. I'm going to call it P prime minus P. So we would have what? MV prime minus MV. So anybody have what that is? Save me a calculator. Go ahead, Chris. So 14.36 and I guess negative, right? Anybody else? Can I get a double check on that? Yeah. So you'll notice, by the way, impulse is kilograms meter per second. Another unit that you'll see, so this is our answer to A, right? Another unit you'll see for impulse sometimes is Newton seconds, right? Because if impulse is force times delta T, it should be Newton seconds. I just want to show you real quick that they're the same thing. Remember, a Newton is a kilogram meter per second squared. And if I multiply that by a second, then I cancel one of the seconds out and it's the same unit, right? So units for impulse are either Newton second or kilogram meter per second. Okay with that? The last part of the problem is the easy part of the problem. So in this case, the F should be J divided by delta T, or negative 14.36 kilogram meter per second, divided by 0.0007 seconds. And that'll give me units of kilogram meter per second squared, which is a Newton. Anyone have a number? Sorry, 20,507. Anybody else get that? All right. Any questions? All right, see what you can do with 2. Okay. This sort of problem is actually not hard once you've seen how to do it. But you got to think about it creatively to figure it out. Anybody see a way we might do this? Anyone have a guess about which equation we're going to use? There's a few ways to do this, but I'm going to suggest this one, right? I'm going to suggest using that equation. All right. I want to maybe knowing now that that's the equation, I want you to see if you can think about this a little bit more. Maybe talk to your partner, see if you can make any headway on this, and then we'll discuss it here in a second. If I have an idea they think would be worth trying. I need to, yeah, go ahead. Ah, interesting. Yes. And why is that incorrect? Why is that wrong? Close. Kilogram meter per second squared is actually a Newton. Yeah, so that's actually, so that's what I would call, the hand waving way to do it, right? It turns out it's gonna work, but it becomes a little bit opaque, like, we're just gonna randomly multiply these two numbers and we're gonna get it. So I wanna kind of dig a little bit deeper into that, but you're right to sort of look at the units and see how they work. Anybody else have anything else they wanna say about this? Because Drake is right. What's essentially going to happen is we're essentially going to multiply these two numbers. But we have to talk about why you can do that. Here's what the way that I would think through it. The way I would think about it is I'd say, let's watch this for 1 second. Or it could be any amount of time, but just for the sake of simplicity, let's say that I'm going to watch this for 1 second, right? In 1 second, how much water comes out of the hose? 1.5 kilograms, right? And it's going at an initial speed of 20 meters per second, and probably, at least in the X direction, right? If it hits the car, that's supposed to be a V prime, not a V1. So once it hits the car, right, it's probably going to come to a stop. So at this point, we can do this, right? Because at this point, this equation becomes, so delta P is just M V prime minus MV divided by delta T. So we just plug in. I think it's 30 newtons. So when you're given something like this in terms of kilograms per second, this isn't the only way. The only time that you might do this is a trick that it's good to have in your back pocket sometimes. But whenever you've got something like this where you know how much is happening per second, and if it's, as long as it's consistent, let's just watch it for a second and see what happens. If you watch something for a second, what's going to happen in this case is 1.5 kilograms of water is going to come out, right? So now we know that if delta T is 1, M is 1.5, and then we can go from there. Now this becomes mathematically equivalent to what Drake was suggesting we were doing, which was just multiplying 1.5 and 20. And he kind of realized that just by looking at the units, but that kind of gives some insight into how that works. Go ahead. Sorry, I forgot about the negative. It's negative the way that I've defined it because I've said that I started going in the positive direction, so yes. Anything else? All right, to round it out, my hint for number 3 is that number 3 is a conservation momentum problem, so it's kind of like what we did last time. But it's another one that there may have to be a little bit of creative thinking going into it. But see what you can do with number 3. All right, this is my attempt at drawing a cannon and a cannonball, right? It gets the job done. Anybody got an idea how we want to do this? Okay, what you thinking?
So I don't know if I'm understanding this, but I just solved for the momentum of the cannonball and then divided that by the mass of the cannon.
So again, I would say that you are essentially doing the right thing. I'm gonna kind of tell you the same thing I told Greg. That would be what I would say is a hand waving solution, in that it works and it sort of makes sense that you can do it. But I want to kind of be a little bit more explicit in terms of why that works.
Well, after looking at the diagram, they're not moving at the beginning. Their total momentum has to be 0. So at the end, they need to be moving in opposite directions, and the momentum has to be decreasing. That way it cancels out.
So if we think about this as a conservation of momentum problem, right? what we're in essence saying is that the momentum of everything here should be equal to the momentum of everything here, right? Yeah. At the beginning, how much momentum do I have? None. At the end, I've got the momentum of the cannon, and I have the momentum of the cannonball, right? So in other words, I have 0 equals the mass of the cannon times the v prime of the cannon plus the mass of the ball times the v prime of the ball. So what? V prime of cannon should be negative mass of ball v ball prime divided by mass of cannon. Questions? I did it again. There we go. It's recoiling, right? So it should be going backwards. Another thing I like about this recoil problem is it reminds us something. Does anybody remember which law the conservation momentum came out of? The third law, right? Conservation momentum comes out of the third law. If you explain, we could have explained recoil before this unit, right? We would explain recoil as if the cannon wants to put a forward force on the ball, then the ball has to put a backward force on the cannon. That's how we would have explained it, just using the third law as we talked about before. Conservation of momentum is saying the same thing, but it's saying it in a different way. It's saying that in order to maintain 0 momentum, if the cannon gives the ball positive momentum, the ball is going to have to give the cannon negative momentum so that the total momentum of the system still cancels out to 0. Yeah.
So I was thinking about this at the beginning of the problem, like, there's no gravitational potential energy or current potential energy. So is there like other types, like in the gunpowder or whatever?
Yeah. So what you would have is you would have chemical potential energy in that case. Yes. Yeah. So if you talk about this conservation energy, you have to have an equation for talking about what is the chemical potential energy that gets converted to kinetic. Any questions about any of these? Let me make sure that I didn't have anything else I wanted to say here. Let me look at my agenda. Yep, we did all that. So you got work time on your syllabus. So here's things that you can be working on right now, right? So project sources, I think I got a few of you turn them in on Thursday when we did it. But just have them turned in by Friday. So remember, 3 sources, cited in APA style, with a short summary for each source of what information you're getting from that source. Like I said, I've got all the due dates I planned out this whole unit, so I have all the due dates already in your syllabus. But at this point, those first 2 sections you can have done by Monday. And the other thing is, if you'd like to do test corrections, in a minute I'll hand back your pre-response part of the test so you can look at it. But it should be already set online. You can pull up test corrections. For those of you who are maybe new to the class, to my class, I store test corrections in the same chapter. So if you go back to chapter 6, work energy, and you go down here to chapter 6, test corrections, it tells you how to do corrections, and it gives you a link to the test. at this point, sorry, I don't mean to show grades, my bad. So at this point, right, you can, when you click on it, you'll be able to see how you did. It should allow you to go in and see which one you missed. And then you will, all right? Any questions? All right, that's all I got.